Good afternoon, class. I'd like to begin with a quick as I can review of some of the main concepts from last class. And last class I brought up my chart of the standard model. That is our chart that physics thinks that's everything in the universe. Anything you call stuff, we physicists think it's made of those things. And like I said last class, it's even simpler than that. The things that you and I are familiar with, it's really just three of those things make up the things that you and I call stuff. So up quarks, down quarks, and electrons, that's what you and I call stuff. Now, what's special about that chart represents the 17 ways that we've found that if you keep drilling down, you're not going to get any smaller. Those are fundamental particles. And so when you get down to the fundamental scale, what differentiates things isn't things like size or color, shape, smell, taste, anything like that. And in fact, these can't even have size. In order for us to really determine something's size, it has to have a right and a left or a top and a bottom. If you're down at the fundamental scale, you can't have a top and a bottom because one particle would be the top, the other particle would be the bottom, and you'd call that the size. These are basically sizeless. Really, they're point particles. So what does distinguish them? There's really only three properties. Mainly, there's only three properties that distinguish these things. And these are the fundamental properties of the world, or of our universe. So when I look at something in the universe and I can distinguish it by its size or color or something like that, that's not fundamental. Its size or color, things like that, those arise from other fundamental quantities, other fundamental behaviors. So what I call fundamental, there's really just three. And it's mass, charge, and spin. And we're not going to worry about spin in this class. So the difference between any of those, pick a Higgs boson and a tau neutrino, the difference is mass, charge, and spin. Mass, hopefully we're pretty familiar with. Mass is that thing that we've been talking about a lot this semester. It's stuff. If something has stuff, it has mass. And one of the things, the concept I brought up last class that I want us to be now very familiar with is the idea of fields. And these two fundamental properties, mass and charge, they create fields. And so this fundamental property called mass actually creates an area of influence around it called a field. So if I have a mass, I don't know, something like a planet, it doesn't need to be that big, but we'll go with a planet. If I have a planet, it creates an area of influence around it that we call a gravitational field. That area of influence extends out to all infinity. Now, one thing I didn't mention last class, I want to make sure we understand today, is that here's one of the most important things you can know about a field. What a field does is it pushes or pulls on other similar particles. And by similar, I'm meaning just having that same property of mass. So there's the Earth. Like I said, it could be anything. It could be just a proton. Anything with mass creates a field around it. That field will push and pull on other things with mass. So the reason you are sitting in your chair right now, the reason you feel this thing called weight, it's because one way to think of it, and this is how a lot of physicists think of it, is you're in the presence of a gravitational field. There is a field in this room right now, and the gravitational field is pointing down. You can imagine a bunch of downward pointing arrows in this room. You have that thing called mass which responds to gravitational fields. If you could be a person and have all kinds of properties, and if you didn't have that thing called mass, I don't know any people that don't have mass, but if you didn't have that thing called mass, you would not respond to this gravitational field. So one way to think of mass is that thing that responds to gravitational fields. So your weight is that F equals mg up there. Your weight is the product of the fact that you have mass and you're in the presence of a gravitational field. So there's a force, an actual physical pulling that's occurring on your body right now that's a product of those two things. It's a product of the fact that you're in a field and you have mass. Okay. That is a very good analog to what we need to talk about next, and that's electric fields. And so hopefully you can see my analogy. The picture is very, very similar. I've switched to red. Why not? So I've got a charge in the universe. So again, I like to imagine just a perfectly empty universe, put a charged object in the middle. That charged object does just like the planet does, creates a field around it. It's not a gravitational field, it's an electric field. So that charged object creates an electric field around it. I've chosen a negative charge just because I wanted the arrows to be toward the thing, because those arrows indicate the direction a positive charge would feel. I don't have to indicate plus or minus when I'm talking about gravity. We're pretty sure there's no negative gravity, so everything's just attractive. When we're talking about charges, it's easy to find a positive and negative charge. Proton, neutron, or proton, electron, there's your example. So here's my negative charge. It could be an electron. It could be a big negatively charged planet. I don't know. But it's just a big negative, something with a net negative charge. And in this universe, the way you give something a net negative charge is you either make it an electron or give it some extra electrons. So you and I right now are pretty neutrally charged. That doesn't mean we don't have any charged objects. We have trillions of them. It's just that they all balance out. So I right now have probably roughly the same number of protons and electrons, so my net charge is roughly 0. Take an object, add some electrons to it, and there's your negative charge. That negative charge has an area of influence around it. That's called a field. Now, just like mass, one good way to think of a field is something that will push or pull on other objects with an electric charge. So here's the picture of that. I take some negative object, make an electron or something, put it in the universe. What those arrows indicate is what another charged object, a positive charged object, will feel. It'll feel a force. That's what a field does. In fact, there's no way around that. If you are in an electric field and you have charge, you will feel a force. There's no way around that. And in fact, like I said, I'm neutrally charged. I have roughly the same number of protons and electrons. My net charge is 0. But put me in an electric field, all of my charged objects will feel a force, and there'll be a charge separation in my body. That's actually what we saw when we started playing with electromagnetic waves. Think about some of the examples we saw when we were talking about electromagnetic waves. Here's a picture of I don't know, pick one, a photon, a microwave, or visible light, a microwave, something like that, a radio wave. There's a picture of a radio wave. So when a radio wave passes by, I don't know, we'll say this pole right here is my radio antenna. I'm trying to tune in to 106.1 the corner. There's radio waves passing by that antenna. This antenna is full of electrons. Electrons have charge. So when an electric field like that passes by, that charged object will feel a force. F equals QE, Q being the charge. It'll feel a force. And the cool thing about photons is that they go up and down, up and down. And so the electron in my car antenna will feel pulled up, and then pulled down, and then pulled up again, and then pulled down again. And that's what my car radio reads as a signal. So what I want you to see, starting off today, is that with these things called electric fields, which we've already talked about in terms of photons, what they do is they push and pull on charged objects. A couple other examples we saw with with photons. In my microwave oven, if I throw in some aluminum foil or a CD, I didn't want to get into it that much when we were talking about photons, but that's how we fried a CD. That CD had metal. Metal has mobile electrons. Everything has electrons. But the nice thing about metal is they're very mobile. It's easy to push them around. And so I send in my electric field. My electric field is going up and down. So every electron in that CD felt pushed and then pulled and then pushed and then pulled. And that caused the electrons to literally move. They were literally feeling a force, and they were literally moving in response to that force. When I put a cup of water or tea or coffee or something in the microwave, water is a polar molecule, so that when I look at an H2O molecule, it's a little positive on one side, a little negative on one side. So as that electric field goes by, it pulls on the positive and maybe pushes on the positive and pulls on the negative, and then it flips it. And it does this to those nice polar molecules, and I get lots of heat inside my drink. So right now what we're talking about is fields, and fields push and pull on charged objects. Cool? Okay. Now, yes, Julia. Good question. Julia asked, does anything with mass have charge? Let's see. Not a net charge. Do we have massive uncharged? Where's my massive uncharged? objects. No. You cannot. If you have mass, you have charge, but you can it's very easy to have no net charge. So a neutron is the smallest thing I can think of, or neutrino. There we are, neutrinos. That's why they have, yeah. Neutrino means small and neutral. So yeah, neutrinos. So either neutrinos, yeah, okay, that's a couple examples. So, maybe in a couple weeks we'll talk about, definitely in a couple weeks, we'll talk about particle physics. And they shoot things through their detectors. Neutrinos go in straight lines. Yeah, because they're neutral. That's a good clarification. Neutrinos have no mass. Have very small mass and no charge, so they don't get pushed or pulled on. They don't get pushed or pulled on by electric fields. They do get pushed or pulled on by gravitational fields because they have mass. Yeah, a gravitational field will pull on anything with mass. An electric field will pull on anything with charge. Yeah. Good clarification. Okay. Let's see. We're good. Yeah. So that's fields, and up till now, when we've been talking about electric fields, we've been talking about electromagnetic radiation. So the source of electric field in that picture is the photon itself. So the photon is this electro and magnetic field together propagating through space. What we want to do for the next couple of days in this class is slow that down a little bit and talk about what we usually call electrostatics, meaning static, meaning sitting still. So I can make electric fields other than with photons. And so a photon is an electromagnetic field or an electromagnetic particle or wave, an electromagnetic wave flying through space. I can just take an electron, and there I've got fields. So what we can do now is we can actually talk about electrostatics, stationary fields. Let's do that. Let's start with an eye clicker. So here's my eye clicker question. Say hopefully you know you are full of protons, neutrons, and electrons. That's you. Say you and the person next to you just increased the amount of electrons in your body by 1%. So however many electrons I have right now, they just increased by 1%. Me and the person next to me would feel a mutual repulsive force of about 1,000th of a pound. Small but measurable. About 1/10 of a pound, or maybe 10 pounds. Maybe 1,000 pounds. Size of a tiny car. Or the weight of the Earth, which is like 24 zeros after it. Let's take 30 more seconds to decide. A, B, C, D, or E. Five more seconds. Okay. I almost hit stop. There was a moment you guys were flat across. I almost hit stop then. This is awesome. This is my favorite eye clicker yet. If the trend is right, it's over there. I don't know if trends work in multiple choice questions. Let's talk about that. So one thing, if I were to try to parse through this answer, one thing to know is you've got a lot of electrons. You've got trillions and trillions and trillions. You've got a lot of stuff going on. And so you have a lot of electrons. So even a 1% increase would be a lot. That would be a lot. And one key factor about this question is I'm asking about you and the person sitting next to you. So your proximity is, I don't know, a meter or so. And the next thing you need to know, which maybe not many of us know just by heart, is that the force between you is familiar. We've seen a formula like this before. GMM over r squared, that's Newton's law of universal gravitation. We've seen that. The electric force is very similar. So similar, you know we're talking about the same universe. The universe, we happen to live in a universe that does things like that. The mutual force between you and your charged neighbor is proportional to the product of your charges. Just like the gravitational force between you and your neighbor is proportional to your masses. It falls off with r squared, so as I double the distance between me and my neighbor, the force between us will be quartered. And it's proportional to some constant. Here's what's crazy about the gravitational force versus the electrostatic force. Earlier in the year, we talked about you and your neighbor are mutually attracted right now. There's no way around that. That force is almost immeasurable. Capital G is a 0.000000007. That's capital G. It's very, very, very tiny. Capital or lowercase k right there is 9. It's about, do the math, 9 and 11, it's about 20, so that's a million, it's like 100 million times bigger, the electrostatic force. So if you were to increase your electrons by just 1%, your neighbor to increase their electrons just by 1%, the repulsive, like charges repel, opposites attract, the repulsive force between you and your neighbor could lift the entire Earth. It would be that strong. It would be massive, massive, massive. In fact, just to give you a picture of it's so massive, right now, if you were holding anything in your hand, or if there's a machine in your lap, or a pencil in your hand, or a clicker in your hand, whatever it is, think about the battle that's happening right now. Right now, there is something called the planet Earth that wants to pull my phone that way. The entire planet Earth. All of the oceans, all of the continents, all of the stuff in between, all of the people are pulling my phone down right now. I don't think there's much above me. Everything's pulling my phone down. I'm winning that battle just by the electric repulsion between my palm and the phone itself. So the reason my phone isn't accelerating toward the center of the Earth is because the electrons in my phone are repelled from the electrons in my hand. That's it. That's called electrostatic repulsion. Hopefully you've thought, I don't know if you've ever thought about that in your life. Why aren't I accelerating through the floor? I'm mostly empty space. That's mostly empty space. Why aren't I flying through the floor right now? The answer is I'm full of electrons. The floor is full of electrons. We're mutually repelling each other. In fact, if you want your depressing metaphysical thought of the day, here it is. You'll never touch anyone. Sorry. You'll try when just push your thumb and your finger together right now. They're not touching. They're repelling each other very strongly, and your brain is interpreting that as touch. They're not touching. They're repelling each other. There's a gap because both my fingers are covered with electrons, and they repel each other very strongly, so strongly. 100 million times stronger than gravity. You're not sitting in your chair right now. You're floating above it. It's true. So I don't know where that came from, but how do you feel pain? Great question. How do you feel pain? Well, I feel pain in my heart just knowing I'll never touch anyone. But also where pain comes from, let's take, I don't know, I'm not going to stab myself right now. I'll just use a key. But my hand is made of atoms. It's carbon and water and stuff. This key is made of steel, made of atoms. And right now, if I were to push my key in toward my hand actually deflects. I can see it moving. What's happening is the repulsion between this key and my hand are so strong that my hand is actually trying to get out of the way. And if I were to push hard enough, my hand molecules would literally go, okay, and would let go of each other, and would let the repulsion, the electric repulsion of the key would exceed the attractive chemical bonding of my skin molecules. So right now, the only reason I'm have boundaries and I'm not just a puddle on the floor is that my skin is chemically bonded to itself, and so I have structure. But that structure is not infinite. And so you can split anything. You can split a diamond. You can split anything. And what you're doing when you cut a diamond in half, you're just pushing some other object into it so strongly that the diamond molecules go, all right, I'm done. So you can literally just put enough energy into a spot that my skin molecules just say, that's enough. I'd rather not it's just chemical bonding. So my skin molecules want to stay together just only so strongly. And if you shove something in there, they'll let go, but it's without touching. It's just using repulsion. So it sounds crazy. You're floating over your chair. That sounds crazy. But the moon is attracted to the Earth over millions and millions of miles. That just magic attraction through space happens all day long. And so right now, you're magically levitating above your seat. That sounds magic, but it's just as magic as the center of the Earth is magically pulling you down. It's all response to fields that the physics behind that is, I don't know, magical, I guess. Okay. Okay. So you are floating above your seat. So here's the silver lining. So you're never going to touch anyone. That's sad. But we talked about last class, which we're going to talk more about today. You will swap electrons with them, which is nice. So go touch someone, which means just get your electrons in a close enough vicinity with them, and then separate. Chances are you just swapped electrons. Chances are your electrons have no particular affinity to you. In fact, all electrons are 100% identical, so your body doesn't know, hey, that's my electron. So you just swap electron, you do this, do that, and then you've swapped electrons. And so maybe that's your metaphysical high point for the day. So speaking of swapping electrons, last class we talked about the triboelectrics. Yeah, Billy. Billy asked a great question. I don't know if everyone heard that. So you'll never touch anyone, but reproduction happens. Yeah, no, let's see. I would say that's as close as it gets. Yeah. Your DNA merges with somebody, however that whole reproduction thing works. Cells commingling, DNA hanging out, yeah. That's probably as close as it gets. You win. I would write that down. I would say that is the closest we get. We will never touch anyone, but you might create life, which is pretty good. Okay. So, good point. Okay. So I'm not touching this balloon right now, but I am getting it to swap electrons with my shirt. The balloon is made of rubber, which is kind of down on that scale. My shirt, I think, is cotton, which is cotton up there? Yeah, just above. So this will only work okay. If I was willing to rub it on my human hair, that would be better, but I'm not going to do that right now. So I'm going to rub it on cotton. So this balloon is stealing electrons from my shirt. It's not touching, but it is sharing electrons. It is sharing electrons, and so I should be depositing. We'll see if this works. I should be depositing electrons right here. And so if that worked, I can do the old trick. Oh, I might need, all right, fine, I'll do here. Come on. Oh, no. Let's see. It's not working, is it? What is this wall made of? All right. I'm going to cheat. All right, let's see. That should have worked. Yeah, let's try that. Okay. Come on. It's like a magic balloon. Everyone's done this trick, right? You stick balloons to the wall at a party. Has anyone seen it not work? It's amazing. Let's see. Oh, this is positive. I just neutralized it. Let's try that. I should be able to. All right. Well, All right, we're gonna skip that one. I gotta stick something to the wall now. Where's rabbit fur? Okay, that'll work. I have a rabbit fur up here. Why not? Okay. When do I just give up? That's close enough. I'm gonna let that go. Okay. So that is sticking, I swear, it is sticking. It's not sticking enough that it's totally stuck to the wall, but it's sticking enough. Well, I'll give myself credit for that. So what we were just talking about, what I'm talking about is the triboelectric series. And the triboelectric series just determines where, when you do that swapping, how even that swapping is going to happen. And when you're lower on the scale, you end up with more. Let's see, we've got 3 minutes to talk about that. 3 minutes. Okay. So, yeah, real quick. So here's what was happening. Just a couple important points about that failed experiment right there. So the balloon's an insulator. That's an important point. The definition of an insulator, which I don't know if has come up yet in this class, is the electrons are very not mobile. And so when I took that balloon and I somehow got some electrons to stick to it eventually, those electrons are where I put them. So I deposited electrons here. This is just failing. Okay. So those electrons are right here. It's an insulator, so those electrons kind of stay put. And so if this was a conductor, those electrons would run over and probably discharge to me. Because electrons don't like each other. Electrons are negative, like charges repel. So if I put a bunch of electrons right here, they would like to not be near each other, and they'll distribute as best they can. And like I said, if this was a conductor, they would just run all over me. Because it's an insulator, I can sort of deposit them in the same location. And when I deposit them in the same location, there's all my negatives on the balloon. Then here's what happens. And so if you've ever done this at a party, what you're doing is you're inducing charge in the wall. You're inducing charge in the wall. Here's how you're doing that. You take this balloon that now has a spot of negative charge on it, and you bring it up to the wall. The wall, just like everything else, is made of atoms. Those atoms are made of positive and negative charges. Even though the wall is also an insulator, its electrons are not mobile. When you draw the balloon close to the wall, the electrons are going to repel the electrons in the wall. And so even though you've just got little atoms, the electrons in those atoms are going to hang out on the other side more than they hang out on the balloon side. So electrons are always in motion. So what I'm doing is I'm just kind of statistically skewing them away. I'm kind of pushing them out of the way. So they're always in motion. They're just going to hang out more, slightly farther from the balloon. So what I've done, and hopefully you can see in that picture, I've induced a charge in the wall. So I have an insulator versus a conductor. I've induced charge. There's some lingo terminology for you today. Now, once I've induced that charge, you can see that opposites attract. I should be able to stick the balloon to the stupid wall. And because I've got electrons and positive charges, it should stick. Whatever. All right. Let's try one demonstration. Couple demonstrations of that. Okay. The first one, let's see, let's go back to my triboelectric series. Okay. I don't think we got to this last class. I wanted to make sure we saw this. Last class I had some silk way up there and PVC, I think, way down here. So if I take silk and PVC, I'm going to do the same thing the balloon was doing. I'm going to induce, I'm going to move this over here. I'm going to induce a charge in this metal ball. That ball's metal. Because it's metal, the electrons are very mobile. So when I bring this PVC, which is going to be negative, near that, when I bring the PVC near that ball, you should see the ball actually be attracted. And here's why. I'm inducing charge. The negative charges in the rod will chase the electrons away, leaving a net positive charge near the rod, and it'll be attracted. Then, so let's see if I can do that. So I can get it to attract. So I can attract the ball to the rod, but I'm not touching it. So I'm only inducing a charge. But then what happens is when I let the rod touch the ball, I'm not inducing anymore, I'm conducting. I'm going to conduct. And here's what's going to happen when I conduct charge. The electrons in here that don't like each other, they're all negative, they don't like each other, they're going to jump over to that positive area on the ball. Now I've actually, with conduction, I've actually charged that ball. That ball is now net negative, as is the rod, and I can chase the rod away. So I want everyone to see that. So a minute ago, the ball was attracted. Hopefully that's visible. Let's try it again. So I just grounded it, by the way. Ground is the term we use for let all the electrons run to me. Okay, so I just grounded it. It should be roughly neutrally charged right now. So I should be able to attract the ball with this rod. Oh, and now I touched it. Now it's going to be repelled. So that's the process that's going on. There's actually kind of a lot going on there. This is a conducting ball. The electrons are very mobile. I can attract it. Same reason the balloon's supposed to be attracted to the wall. But then if I touch it, electrons are going to jump to the ball, and they'll be, then this is net negative, this is net negative, and they'll be repelled. Like charges repel. I could probably do that with this guy over here in a similar fashion. So for the next 13 minutes, we're going to play with this. That's what my notes say. Play with this for roughly 13 to 15 minutes. And here's why this thing's so fantastic. This is called a Van de Graaff machine. Hopefully somewhere in your science career you've played with a Van de Graaff machine. They're amazing. And here's what they are. They're just fancy ways to take advantage of tribal electrification. I mentioned last class, trib just means rub. And so I'm electrifying by rubbing. And so I've got a belt in here. In this case, the belt is made of rubber. Rubber should be roughly in the middle. And I've got a pulley on the top and the bottom. Those two pulleys are on either sides of rubber on the series. So as that belt goes around, I can actually be yanking electrons off of the top pulley and depositing them on the bottom pulley. Yanking them off the top, deposit them on the bottom. Yank them off the top. And the cool thing is, because this is conducting up here, the lack of electrons always exists on the outside, and it's never on the inside. The electrons always reorganize in such a way I can do that all day long, and I can get a ton of charge up here, way more than rubbing a balloon on my head. And so I can actually get lots and lots of charge to happen just by, so it's a very simple device. There's a pulley, a motor, wow. There's I can't get that close to it. A pulley, a motor, a belt, and then a dome that's just collecting all of the charge. And so I could probably do the same thing, just way better with this. So this guy is neutrally charged, because I am, and I just grounded it. Let's see, I'll stand over here. Yeah. So I should be able to get this thing attracted. It's attracted, I think, and then once it hits, it's repelled. And now I'm not going to be able to get it back on. Now it's going to orbit like a planet. I'm not going to be able to get it to touch again, because this has a, yeah, wow. Because this has a negative charge on it. So again, I'm pretty well grounded. I'll touch something metal. I'm pretty well grounded. I think it should be attracted now. And then once it touches, they're both very, very negative or very positive. I think they're both negative, very, very negative right now. And so now I can't get it. It doesn't want to touch because it's charged up. And then it might eventually start to lose charge up through the string. I can actually feel it discharging through me, and then I might be able to get it to touch it again. And then if I do, it'll be repelled strongly again. So it's not going to be. Okay. Let's do a couple other quick examples. Start with these guys. So yeah, what you're hearing right now, by the way, if you listen, what you're hearing right now, I have to stand away for it to happen, yeah. So I think the top is becoming negatively charged. So the top is being just like piled and piled and piled with extra electrons. Electrons don't like each other. They eventually build up so much repulsion, so much static. By the way, if you've heard, the term static that we've been using our whole life, oh, my clothes have static or whatever. Static just means stationary, and it's short for static electricity. So when your clothes have static, that's all they're doing. They're mutually attracted because of a charge. It's usually extra electrons, and they're attracted. They're like the balloon in the wall is supposed to do. So anyway, this is building up lots and lots and lots of charge, and they get so charged up. This is the same thing that happens in the sky in a lightning storm. You get a cloud so charged up that it ionizes the air, meaning it actually rips electrons off of air molecules, creating a conductive path in the air, and shoots out lightning. And that's what you're actually hearing around here. You're hearing thunder, like baby thunder. And every now and then it gets charged up so much it discharges into the air, and then it has to charge up again and discharge in the air, then it has to charge up again. And that's just baby thunder. Let's see, I could maybe turn the lights down a little bit. We might be able to, I'll turn it all the way off. See if I can see it. Yo, okay. Let's see if those lights are still on. I have to get this thing to charge up enough. Is that visible? I might be able to, hold on. Let's see, let's go to, there we go. There it is. All right. Bad focus. It's autofocus. There's nothing I'm going to be able to do about that. All right. I bet if I go out and back in or something. Or maybe put the lights on. Oh, did it do it? Oh. Okay. Got it. Hey, all right. Now I got to turn lights off, then the focus will go out, right? Try it. And by the way, yeah, isn't that cool? I can get the electronics in the room to freak out. Wait, so it's not gonna work. All right. Come on. Oh, here we go. There, now we're talking. Well, whatever. All right, there's lots more fun we can have with this thing. Okay, I don't need that. Okay. Oh, it's totally shocking my. So here's one example. I have a. Oh my, it's awesome. All right, so okay. So, by the way, that I wasn't supposed to be the example of that because I have potentially. Go. Okay. Jump. Okay. Okay. I have potentially the worst hair, some of the worst hair in the classroom for that example. There's 6 minutes left. Before we do anything else, I definitely need somebody with a foot or so of hair to come up here. All right, let's get a couple people. Come on, let's get like 2 or 3 people. There we go, much better. All right, much better. Huh? Yeah, you did, nice. Okay, so here's how it's gonna work. And by the way, just like all these demonstrations, this needs to be educational. It's not just for kicks. I don't know if I fried this thing. I felt it zap at one point. Okay. Go ahead and stand on my magic stool. Yeah. So that stool is made of plastic. What's your name again? Charlie. So I'm trying to insulate Charlie from ground. So I'm about to cover Charlie with electrons. Those electrons are mutually repulsive. They want to get away from each other. The easiest thing they can do is just jump through his feet into the ground. The earth is a great place to go if you're an electron. You would like to get away from your friends. So they'll all just jump into the floor. But I've insulated him from the ground, so they'll have a hard time doing that. He's a solid foot above the ground on a piece of plastic. So here's how the electrons should behave. He's going to be completely covered in electrons. They're going to want to get away from each other. And all the electrons on all of his hairs, the way they will arrange themselves to be a maximum distance from each other should be like this. We'll see what happens. So go ahead and put your hands on there. It doesn't hurt to put it on the first time. Okay. And then you should. Now it has to overcome the weight of gravity. So it takes a second to get charged up. I think we can see some of them starting to. Let's see. Okay. Yeah, I know it's weird to do this, but give it a shake. Yep. Yep, there it is. All right. So you can see some of them, yeah. Some of them are definitely starting to stand up. That's pretty good. Pretty good. We'll give it a couple more seconds. That might be as good as it gets. Okay. Now let's see. Now what you need to do is pull your hands away and watch. No, it's not going to hurt, I promise. So watch what happens. Watch what happens. When he pulls his hands away, his hair should stay up. So go ahead and, yeah. Now when he steps on the ground, that's when he'll discharge to the ground. So go ahead and step off the stool. And that's when his hair goes down. And you probably felt it go out your feet a little bit? Yeah. Okay. So thank you. All right. Let's see. I'm grounded. Okay. Okay, go ahead. There we go. Here's attempt number 2, and I think we'll have time for 1 or 2 more if someone else wants to try. But all right, go ahead and, there we go. Same deal. She's going to get covered in electrons. Those electrons are going to be mutually repulsive. They're going to want to get away from each other. Okay, there's some right there. Okay, there's one going straight out the back. So, I mean, in a perfect world, they would be radial. I mean, you'd see lines just because the electrons are going to arrange themselves to maximize the distance between them. That's actually pretty great. Yeah. Very nice. That's a good one. That's awesome. Okay, so same deal. Pull your hands away from but stay on the stool. So you can see her hair stays standing up, and as soon as her foot touches the ground, you should see her hair drop down. Go ahead. Yeah. And do you feel it go through your feet? Yeah. Okay. Okay. Yeah. We have time for one more, if anyone else wants to do it. Okay, feel free to come up. You'll see I have other, okay, here's a good one. If no one wants to do it, this is my ideal human right here. That one goes pretty quickly. So that's kind of what everybody looks like. And you can see that nice radial pattern. And here's something cool. We don't have time today to get into details, but if you've ever wondered why you have a lightning rod, lightning rods are sharp, which is the opposite of that dome. A very sharp point will actually create a very strong electric field. And I should be able to discharge this thing with a lightning rod. So this is my lightning rod, and all I have to do is get kind of close, and I can discharge that. So what I'm doing, you can't hear it because they don't have time to build up and make lightning and thunder. That's what you hear. But it's actually the same thing. The electrons are leaping through the air onto this point by me doing that. Okay, we have 1 minute left. Let's see, the last thing I'll do. Let's see. I'll hold up some of these guys, then we'll be done. Yeah. There we go. And same thing, I'm giving electrons, that hurts right there. I'm giving electrons to these styrofoam peanuts. Yeah. And they're mutually repelled from each other. Like that. There we go. Okay. I think we'll call it a day. I have time if anyone else wants to try this.